Namaskar दोस्तों. Today we are going to solve most of the questions of the exercise of thermodynamics. So first question is, a thermodynamic state function is a quantity. Four options are there. State function. There are two types of functions, state function and path function. State function means which depends upon the state of the system. It is independent of the path followed. For example, if we go from ground floor to 7th floor, either by staircase or by accelerator, potential energy remains same. On the 7th floor, it is equal to mgh. So height attained matters. How you attain that height doesn't matter. That means path independent quantity is a state function. It depends upon the state only. So that implies that second option is correct. So 2 is the right option for question 1. Question number 2. For the process to occur under adiabatic conditions, the correct condition is. So what are adiabatic processes? Adiabatic process is the one where there is no exchange of heat. Means between system and surrounding there is no transfer of heat. There is no exchange of heat between system and surrounding. That means for that Q is 0. What is the name of the process in which delta T is 0? Yes, delta T 0 means temperature is constant. So temperature is constant for isothermal process. So first option is correct for isothermal process. What about delta P? Pressure is constant for isobaric process, and work is 0 for free expansion of our gas. Free expansion means when external pressure is 0, because work done is equal to minus P external into for irreversible process. So if external pressure is 0, that means if we expand a gas against vacuum, that is called free expansion, when external pressure is 0. So work done is 0 for free expansion of any gas. So question number 3. The enthalpies of all the elements in their standard states are. Actually, enthalpies of all elements means enthalpy of formation of all elements. So what is enthalpy of formation? Enthalpy of formation is defined as enthalpy change when 1 mole of compound is formed from its constituent elements in their standard state. That means, and enthalpies of all the elements, enthalpy of formation of all the elements in their standard state is taken as 0. This is a conceptual question where enthalpies of formation of all elements in their standard state is taken as 0, means right option is 0. But like oxygen, its standard state is O2 gas. Means standard state means at 1 bar pressure and at constant temperature. Normally we take it as 298 Kelvin, means at room temperature. For example, standard state of carbon is graphite. You know, carbon has two allotropes, diamond and graphite. Buckminster fullerene is also there, but out of graphite, diamond and Buckminster fullerene, graphite is taken as standard state because graphite is thermodynamically most stable allotrope of carbon. Again, standard state of sulfur. Sulfur has different allotropes: rhombic sulfur, monoclinic sulfur, plastic sulfur. Out of all the sulfurs, rhombic sulfur, again it is thermodynamically most stable allotrope of sulfur, is taken as its standard state. Standard state of phosphorus is white phosphorus. There are three types of phosphorus: white phosphorus, red phosphorus, black phosphorus. Though thermodynamically most stable allotrope of phosphorus is black phosphorus, but white phosphorus, it is also known as yellow phosphorus, is taken as its standard state, though it is highly unstable, but because of its abundance, it is taken as the standard state of phosphorus. So standard state of phosphorus is white phosphorus, and enthalpies of all these elements in their standard state is taken as 0. So keep in mind this thing. Now come to the question number 4. This knot represents standard internal energy change of combustion of methane is minus x kilojoule per mole. So what is the value of delta H naught? Means how delta H naught and delta U naught are related. So see, whenever we have a question like this, first of all write the equation. Now, combustion of methane. Methane, formula of methane is CH4 gas. So when it burns, carbon turns into carbon dioxide gas and hydrogen into H2O liquid. There are 4 hydrogens, so it is like this. Now you can look at this equation: carbon 1, carbon 1, hydrogen 4, hydrogen 4. What about oxygen? 2 oxygens, 2 into 1, 2, 4 oxygens. So there is 2 O2. Now what is the relation between delta H and delta U? You know, delta U naught is standard internal energy change. Delta H naught is standard enthalpy change, and they are related as delta H naught is equal to delta U naught plus delta Nj RT. Now, delta Ng decides the relation between these two. If delta Ng is less than 0, means negative. If delta Ng is negative, then delta H naught is less than delta U naught. If delta Ng is greater than 0, means positive, that means in first case something is subtracted from delta U naught to obtain delta H naught. But here delta Ng is greater than 0 means delta Ng is positive. That means something should be added to delta U naught to get delta H naught. That means delta H naught is greater than delta U naught. And if delta Ng equal to 0, then this whole term is 0. So delta H naught is equal to delta U naught. Right? Now come to this part. What is delta Ng? This delta means change, N means number of moles, and G means gaseous moles. So this means change in gaseous moles of the reaction. So change is between product minus reactant. Number of gaseous moles of the product minus number of gaseous moles of the reactant. On product side, CO2 is gas, but H2O is liquid. What it means? There is only one gaseous mole. So product has one gaseous mole. Now come to this part. CH4 is gas, O2 is also gas. So total number of moles, 1 mole of methane and 2 moles of O2. So total 3 moles. So 1 minus 3 means become minus 2. It means delta Ng is less than 0. So delta H naught is less than delta U naught. So that means right option is 3. So question 6 is a reaction A plus B to give C plus D plus Q. A plus B to give C plus D plus Q. That means heat is added towards product. It can be written as A plus B to give C plus D delta H equal to minus Q. That means this is exothermic reaction where delta H is negative. Plus Q on product side means reaction is exothermic because it can be written as this. Now it is found to have positive entropy change. That means delta H is negative, delta S is positive. And you know, to see the feasibility of the reaction, we take into account delta G, and delta G is related to delta H and delta S by this relation. This is Gibbs-Helmholtz equation. According to this equation, if delta G is negative, reaction is spontaneous. If delta G is positive, that means reaction is non-spontaneous. And if delta G is 0, it means reaction is at equilibrium. Spontaneous means which can take place by its own, or reaction is possible. Non-spontaneous means which cannot take place by its own. It needs the help of external agency to take place. That means this type of process or reaction is not possible. Equilibrium, you know, means reaction is still. It cannot go on either side. So now come to this part. Delta H is negative and delta S is positive. That means this part with negative sign, negative means this reaction has negative delta G at any temperature. It has negative delta G at any temperature. That means this reaction is possible at any temperature. So that's all. That means fourth option is correct for question number 6. Question number 7 is, in a process 701 joule of heat is absorbed by a system and 394 joule of work is done by the system. So what is the change in internal energy for the process? So you know, according to first law of thermodynamics, delta U equal to Q plus W. This is mathematical form of first law of thermodynamics. Delta U is change in internal energy. Q is heat absorbed or released. If heat is absorbed, its sign convention is positive. If heat is released by the system, then sign convention is negative. So Q is negative when heat is released by the system. Q is positive when heat is absorbed by the system. Now come to the W. W is work done. If work is done on the system, then W is positive. And if work is done by the system, then work is negative. So these are the sign conventions. Heat released by the system, negative, because heat is taken out of the system. Heat absorbed by the system, heat is added in the system, so it is positive. Work done on the system means work is done by the external agency on the system, so it is positive. And if work is done by the system, that means W is negative. Now come to this question. 701 joule of heat is absorbed. That means it is positive in joule. Work is done by the system. By the system is negative. So minus 394. Q is plus 701 joule. W is minus 394 joule. In this way, means you can write Q is plus 701 joule as per sign convention, because heat is absorbed by the system, and work done is minus 394 joule because work is done by the system. So in this way, 701 minus 394, so it comes out to be 307 joule. So change in internal energy is 307 joule. So question number 9. Question is, calculate the number of kilojoule necessary to raise the temperature of 60 gram of aluminium from 35 to 55 degrees Celsius, and molar heat capacity of aluminium is given to you. And you know the relation between molar heat capacity and heat. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So according to formula, molar heat capacity equal to heat divided by number of moles into change in temperature. This is the exact formula. Now we have to calculate number of kilojoule necessary to raise the temperature of 60 gram of aluminium from 35 to 55 degrees. It means we have to calculate Q. So Q is equal to N into Cm into delta T. So as per the formula, molar heat capacity is 24 joule per Kelvin per mole. Change in temperature is, final is 55 minus 35 means 20 degrees Celsius, and you know change in temperature is same in degrees Celsius as well as Kelvin. Now N is number of moles. So number of moles is mass over molar mass. Mass divided by molar mass. Mass, number of moles of aluminium. So mass of aluminium is 60. And what is molar mass of aluminium? It is 27. It is 60 gram divided by 60 gram per mole. If we divide 60 by 27 by 3, it comes out to be 20 by 9 mole. So Q comes out to be N is 20 by 9. Molar heat capacity 24. So to calculate Q, N is 20 divided by 9 mole into molar heat capacity, that is 24 joule per Kelvin per mole, and delta T is 20 Kelvin. So in this way, mole per mole cancel, Kelvin per Kelvin cancel, we get 20 into 24 into 20 divided by 9 joule. So by solving this equation, it comes out to be 1065.6 joule, or in kilojoule it comes out to be 1.06, it will be 6 kilojoule. So in this way we can solve it. So question 11 is enthalpy of combustion of carbon to carbon dioxide is minus 393.5 kilojoule per mole. So first we have to write down the equation. You know, carbon to carbon dioxide. So carbon to carbon dioxide gas, carbon is solid, and enthalpy of this reaction is minus 393.5 kilojoule. So see, it is enthalpy of combustion of carbon. That means amount of enthalpy or energy released when 1 mole of carbon is burnt in excess of oxygen. So you know, 1 mole of carbon when burns in excess of oxygen, it gives 1 mole of CO2. So at the same time, it is enthalpy of formation of carbon dioxide. That means 1 mole of carbon when burns in excess of oxygen, we get 1 mole of CO2. That means this value is enthalpy of formation of CO2. Enthalpy of combustion of carbon is equal to enthalpy of formation of CO2. Because what is enthalpy of formation? Amount of enthalpy change when 1 mole of compound is formed from its constituent elements in their standard state. So see, heat released upon formation of 1 mole of carbon dioxide means 44 gram of CO2, because molar mass of CO2 is 44. So heat released upon formation of 44 gram of CO2 is equal to 393.5 kilojoule, right? But we need heat released upon formation of 35.2 gram of CO2. So heat released upon formation of 35.2 gram of CO2. See, we omit negative sign here because we write here heat released. When we write heat released, it is obvious that it is minus. But there is no need to write here. Reason being, we mentioned that this is the amount of heat released, right? Because negative sign is the sign convention for the release of heat. Next, now 393.5 divided by 44 into 35.2 kilojoule. So in this way, when we solve this equation, the value comes out to be 314.8 kilojoule. So in this way, we can solve this question. So our question is, calculate the enthalpy of reaction. So question is, calculate the enthalpy of reaction. Given है enthalpy of formation of CO, N2O4, CO2 and N2. So see, we given values are enthalpy of formation of these molecules. So keep in mind, enthalpy of reaction is equal to sum of the enthalpies of product minus sum of the enthalpies of reactant. So now product is 1 mole of N2O and 3 moles of CO2. So enthalpy of reaction equal to 1 into enthalpy of formation of N2O gas plus 3 into enthalpy of formation of CO2 gas. This is sum of the enthalpies of products minus 1 into enthalpy of formation of N2O4 plus CO. How many moles? 3. So 3 into enthalpy of formation of CO gas. So just put the values. 1 into enthalpy of formation of N2O is 81 in kilojoule plus 3 into enthalpy of formation of CO2, it is minus 393 minus 1 into enthalpy of formation of N2O4, 1 into 9.7 plus 3 into minus 1. You see, just solve it. 81 minus 1179 minus 9.7 minus 330. So in this way, it comes up to be, it is minus 1098 minus 3 to 0.3. So it is minus 1098 minus minus plus 320.3 comes out to be minus 777.7 kilojoule. Roundabout it is minus 778 kilojoule. The question is given N2 gas plus 3H2 gas to give 2NH3 gas, and enthalpy of standard enthalpy of this reaction is minus 92.4 kilojoule per mole. So what is the standard enthalpy of formation of ammonia gas? So first understand what is standard enthalpy of formation. So standard enthalpy of formation is the amount of enthalpy change when 1 mole of compound is formed from its constituent elements in their standard state. So means ammonia gas. To prepare 1 mole of ammonia gas, and two elements are N2 gas and H2 gas. And to balance it, because we should form 1 mole of ammonia. To prepare 1 mole of ammonia, N2 required is half mole and H2 required is 3/2 moles. Now compare this equation. If this equation is divided by half, we get this equation, and this is enthalpy of formation of ammonia gas. So divide given equation, this one, by 2, we get equation for the formation of 1 mole of ammonia gas from its constituent elements in their standard state. So the operation which we perform on the equation, same operation should be performed on the enthalpy. That means enthalpy of formation of ammonia is equal to enthalpy of reaction of the this equation, enthalpy of reaction of this equation divided by 2. So enthalpy of formation of ammonia gas equal to minus 92.4 divided by 2. So value comes out to be minus 46.2 kilojoule per mole. So this is enthalpy of formation of ammonia gas. So this is the question number 13. Then let's go ahead. Question number 16 is, for an isolated system, delta U is 0. So what will be delta S? So you know, delta U is 0 for an isolated system because there is no exchange of energy or heat with the surrounding. That's why delta U is 0. But you know, according to second law of thermodynamics, for an isolated system, in case of spontaneous reaction, delta S is greater than 0. It tends to increase in a spontaneous reaction. So delta U, though delta U is 0, but delta S is greater than 0, or we can say delta S is positive for a spontaneous reaction. In case of isolated system. That's it. So question is, for the reaction 2A gas plus B gas to 2D gas, delta U 298 is minus 10.5. That means it is delta U not, it is standard entropy, standard internal energy change, that is minus 10.5 kilojoule per mole, and standard entropy change is minus 44.1 joule per Kelvin. So calculate delta H naught for the reaction and predict whether the reaction is spontaneous or not. So first let us calculate delta H naught. So delta H naught, that is standard enthalpy change equal to standard internal energy change plus delta Mg RT. So you know delta U naught is given delta Mg for the given reaction. Delta Mg equal to change in gaseous moles of product minus reactant. So for product, gaseous moles are 2. For reactant, gaseous moles are 2 plus 1 means 3. So delta Mg comes out to be minus 1. Now T, it is given 298. So temperature is 298 Kelvin. And what about R? So R is 8.314 joule per Kelvin per mole. But you know delta U naught is in kilojoule. So R should be in kilojoule. So 8.314 into 10 raised to power minus 3 kilojoule per Kelvin per mole. So just put the values. It is minus 10.5 plus minus 1, delta Mg is minus 1 into 8.314 into 10 raised to power minus 3 into 298. So just calculate the value. So this value comes out to be, just calculate it. It is minus 2.478. So add these values. 12.978. It is minus 12.978 kilojoule. So value is delta H naught. First question is calculate delta H naught, standard enthalpy change, that comes out to be minus 12.978. Now second is predict whether the reaction is spontaneous or not. So to predict spontaneity of the reaction, we have to calculate delta G naught. You know, free energy change, if it comes out to be negative, reaction is spontaneous. If it comes out to be negative, reaction is spontaneous. If it comes out to be positive, reaction is non-spontaneous. And if it comes out to be 0, then reaction is at equilibrium. So just calculate the value. You know delta G naught is delta H naught minus T delta S naught. delta H naught we have calculated. Value is minus 12.978 in kilojoule. Keep in mind it is in kilojoule. Minus T is 298 into delta S. Delta S value is minus 44.1, but it is in joule and we need the value in kilojoule because this value is in kilojoule. So just write minus 44.1 into 10 raised to power minus 3. Right? Just like this, R is in joule, we convert it into kilojoule, we multiply it by 10 raised to power minus 3. Same here, delta S naught is in joule, to convert it to kilojoule, we multiply it into 10 raised to power minus 3. Minus 12.978 minus plus, multiply these values, 13.112, it is 0.164 kilojoule. So value comes out to be positive. That means reaction is not spontaneous, as delta G naught is positive. Reaction is non-spontaneous, right? The question number 20 is, the equilibrium constant for the reaction is 10. Calculate the value of delta G naught. R is given, T is given. So we know that delta G naught is equal to minus 2.303 RT log of K. This is the relation between delta G naught and equilibrium constant. So all the values are given to you. If you know the formula, you can get the answer. R is 8. And what is temperature? T is given 300 and log of K. So log of 10. You know log of 10 is 1. So this is so simple. Minus 2.303 to 8 into 300. So it is minus 5527 joule per mole. That implies it is minus 5.527 kilojoule per mole. That's it. So this is the answer of question number 20. Question is, comment on the thermodynamic stability of NO and NO2. Equations are given, their enthalpies are given. So you can see in first case, when N2 and O2 combine to give NO gas, enthalpy of reaction is positive. So in first case, standard enthalpy of formation is positive. That means an enthalpy of the product, because it is equal to sum of the enthalpies of product minus sum of the enthalpies of reactant. That means enthalpy of product is greater than enthalpy of reactant. So as enthalpy of product is at higher end and enthalpy of reactant is at lower end, that means this much heat is absorbed by the product. That means product is thermodynamically unstable. So this one is NO is unstable in nature. But when NO is converted into NO2, energy released is minus 74. And that means when NO is converted into NO2, energy is negative. What it means? That enthalpy of the reactant is more than product. That means enthalpy of product is less than reactant. So this product is stable in nature, right? Graphically we can explain it. See, let us take N2 and O2. Average enthalpy is at this end, half N2, half O2, whatever. This is reactant. So 90 joule of heat is absorbed. This is NO gas, and when this NO gas is converted into NO2 gas, it comes down by 74 joule. That means NO2 is at lower end, NO is at a higher end. That means NO is thermodynamically less stable, or we can say unstable, and NO2 is thermodynamically more stable than NO, or NO is thermodynamically less stable than NO2, right? Question is, calculate the entropy change in surroundings when 1 mole of H2O liquid is formed under standard conditions. So delta H naught is minus 286 kilojoule per mole. So this is the enthalpy of the system. This much heat is released by the system. So if this much heat is released by the system, how much heat is absorbed by the surrounding? Same. So that implies delta H naught of surrounding is equal to minus of delta H naught, right? So it is minus of minus 286 kilojoule per mole. That implies it is plus 286 kilojoule per mole. Now, temperature is not mentioned, but you know, under standard conditions, temperature is taken as 298 Kelvin, and as per equation, delta S of surrounding is equal to delta H naught of surrounding divided by T. And what is delta H surrounding? It is 286 kilojoule per mole. And what is the temperature? It is 298 Kelvin. So in this way, delta S naught surrounding comes out to be 0.959 kilojoule per Kelvin per mole, or 959 joule per Kelvin per mole. That's all for the day.